guys, welcome to a new video in the Opencv hands-on series. Today we'll be making our own hand recognition program. So there are a couple of changes from the last video. In the last video I typed out my code. Since the code wasn't that long, it was only 20-30 lines of code, but today in this program the code is about 100 lines of code. So and explaining each and every line and typing will take a lot of time, so I've pre-typed the whole code here, but I'll be explaining each and every line, so hopefully it'll be all clear. Okay, all right, I'll attach the link, the GitHub link, in the bio, so if you want to check that out after seeing the whole video, please do that. And a humble request is to watch the whole video, otherwise it won't be easy to comprehend the code. All right, so yeah, let's start. So first of all, I opened my IDE PyCharm and I imported my libraries: import numpy as np, import cv2, and import math. So these two libraries, numpy and cv2, were there in the last video as well, but in this particular program we are using the math library as well. This is because we'll be making use of some mathematical functions that will be used when computing what is shown on what you show on your webcam. All right, so that's for a later part, but we need that library, so we're importing that. Next up, we're capturing our video feed from our webcam. This 0 signifies that we are getting our video feed from our webcam. There are different numbers for different sources of feed, but since the primary source for a video is through a webcam, we are passing the parameter 0 to the video capture function. All right, now next up, while our capture is open, this means that this is just a checking of truth. So like this is true, then it'll go into the loop. So this is true, so that means that unless and until you close your webcam, this whole loop will run. All right, so this is true. Then we are writing this line of code where it is written that it is cv2.wait key, and in the bracket you have a 225. So what this does is, there after every 225 units of time your frame is captured. So after 225 units of time your new frame is captured. All right, so this is just a delay. So we give this delay due to the dynamic and continuous video feed, and we need a stable output, right? So that's why we give it a slight delay. Now next up, we get two values called return and frame, and that is equal to capture.read. So as mentioned in the last video as well, capture.read basically reads your frame, your snapshot of your video feed that you get, and stores it into the variable frame. And return, ret, is just a variable that is used to check the truthfulness. We'll just use it in our if condition or loop or whatever to just make the block run. All right, there is no other significance of this variable apart from the truthness. Okay, so next up, we are writing this line of code where we've written cv2.rectangle frame, and so we'll make this, basically this line of code basically makes a rectangle across our frame from the coordinates 100, 100 to the coordinates 300, 300, and we want the color of this rectangle as white. Hence we've written all the values at 255, 255, 255. If you don't know what the RGB notations mean and how you write that, please check out my video on digital image basics where I've covered this topic in detail. I'll put the I banner on top. If you haven't checked that out, please check that out, so that'll be of more help. All right, and next up, this one signifies the thickness of the rectangle, which is 1 pixel thickness. So next up, we're cropping our image. Basically I only want my image that is in the rectangle. So this crop image is basically slicing my frame from 100 to 300 on x and y coordinates. All right, so what this crop image does, it will only get our image of that rectangle. All right, we don't need the rest of our part, that's why. Now next up, we are applying Gaussian blur. So Gaussian blur is basically a function named after a mathematician Gauss that reduces our image noise and detail. We use this to blur our image to reduce our noise. Okay, so we apply Gaussian blur to our cropped image, and a parameter is a 3x3 kernel. So we use a 3x3 kernel as well, and we store the blurred image in the variable named blur. Next up, we convert our blurred image from BGR to HSV color format. So we use cv2.convertColor blur, and our image is blur, and we convert that from BGR to HSV, and we store that value in HSV. Next up, we're masking our HSV image with our values. So this np.array both represent the lower and upper range of skin color. Basically, since we're recognizing our hand, we need to let the program know that these ranges of numbers correspond to our skin color. So this would vary for person to person, but this is just a general range that I've used. Alright, so I googled this range. It's available on the net. You can just google whatever range corresponds to your skin color. Okay, and I've stored that in the variable mask2. Next up, I've defined a kernel of ones, and its size is 5x5. So it's basically a 5x5 matrix full of ones, and this kernel will be used for dilation and erosion. So what dilation does is, so first of all, we dilate our mask2 image, right? Yeah, we dilate our mask2 image with our 5x5 kernel, and we only pass one iteration of that, and we store that in dilation. So firstly, we add some pixels by dilating our image, and then we next up erode our image by removing some pixels. So this basically is done to sharpen our image. All right, so it's done to filter out. So it's basically a method of filtering. All right, I've put the comment here. So we firstly add some pixels by dilation and then remove them by erosion to filter out the noise. It's a filtering process to remove the noise. And so after doing dilation and erosion, we store the filter, we apply Gaussian blur once more to remove any other noise that may be present, and we store the value in the variable filtered. Okay, so next up, we define two variables called ret and thresh, and we pass the cv2.threshold function, and we pass the source image as filtered image. All right, so we're passing our filtered image as a parameter. And so what threshold is basically, so threshold is like the name suggests. So if a pixel value is greater than your threshold value, then that means that the color assigned to that pixel is either black or white, and all the pixels that have the value corresponding, say for example, we give a threshold value as X. So all the pixels that have value greater than X are assigned one color, say black, and all the pixels having value less than X are assigned a different color, say white. So basically what threshold does is it converts our image to a black and white image. All right, so, and again ret is just that boolean variable used to check truthfulness. Okay, so next up we show our thresholded image by passing thresh. So when you run this up until this program, you would see a thresholded image that is only made up of black and white. Okay, so next up, what we are going to do is, since we are placing our hand in front of our webcam, we need the program to identify contours. So what exactly is contours? So we use this cv2.find contours. So contours are basically a curve joining all the continuous points along a boundary, and all those points that are being joined have the same color or intensity. So since you put your hand in front of your webcam, it plots a curve around all your fingers. Since your fingers are having the same color intensity, it plots a contour around them, right? So we're going to be using the cv2.find contours function, which we are passing a threshold image in this function, and a threshold image is it's preferred to use a threshold image because it's basically related to accuracy. So for threshold images, you have a highly accurate contour. So that's why we first converted all our image to threshold, and we are passing that to our find contours function. And in Opencv, finding contours is like finding white object from your black background. So remember, to make the object white and the background as black. Alright, so that's it. So cv2.find contours returns two variables called contour and hierarchy. So here cv2.return ret tree is basically a retrieval mode for our contours. Okay, you can google the specifications by reading the documentation, but this is a kind of retrieval mode. And cv2.chain underscore approx underscore simple is just used for removing the redundant points along the contour, and it compresses our contour. So basically this is just used for saving memory. Okay, and after passing this function cv2.find contours, we get two variables called contours and hierarchy. Alright, so next we are going to be using the try and except block in our Python code. So next up we use this contour equal to max of all the contours in our thresholded image, and we're using the key equal to lambda x. So what this means is that lambda x means an unknown function which basically checks all the contours for that area and returns the maximum contour, right? The contour with maximum area, that's what it returns. Now next up what we are going to do is we are going to be making a rectangle around our contour. So we use the cv2.bounding rectangle and we pass our contour. This contour is the contour with our maximum area, right? And we assign the coordinates as x, y, w and h. So x and y correspond to the top left coordinates, and w and h correspond to the width and height from those coordinates. Okay, and next up what we are doing is defining a hull using the cv2.convex hull function. So what this does is basically hull means the exterior of or the shape of an object. Therefore the convex hull of a shape or a group of points is a tight fitting convex boundary around the points of the shape. Alright, so that's what this convex hull does. Googling will help this part to understand a better graphical image that will make it easy to visualize what a hull means, but once I run this code I'll show you what a hull means. Alright, so next up what we're doing is we're using the np.zeros function to make a drawing. So what this does is we're passing np.zeros and we are filling our region of zeros with the dimensions of our crop image, and we're using the np.unsigned integer 8 data type. So that means this is a data type that ranges from 0 to 255, and in this region the dimensions of this crop image we are filling everything as 0. Now if you know, everything as 0 means black color. So what this line of code basically does is it fills a particular region with only black color. Alright, and we're assigning the variable to that as drawing. Okay, next up we're drawing our contours in our drawing image, and so we first of all we draw the contour of maximum area, and we're using the color green since blue and red are 0 and green is 255. So contours are identified as green color. Next up we're drawing our hull around that drawing variable, which is our black background, and we're drawing the hull with a red color BGR, right? So by these lines of code we're drawing our contour and hull. Next up we're going to be finding convexity defects. So what do you mean by defects? Let me show an illustration. So say this is your hand, right? This is a rough sketch of your hand. So all the points marked in red are called as defects. Basically the voids or empty space between your fingers is called as defects. Okay, so those are defects. So we'll be using the cv2.convexity defects function and passing our contour and hull as parameters, and what it returns is it returns the defects. So the output of this function cv2.convexity defects is it returns an array where each row contains these values. So you have 4 values returned in a form of an array, and those are starting point, ending point, farthest point and approximate distance to farthest point. So we denote that by SEFD, starting, ending, farthest and distance. Alright, and so we denote it like that, the output that we get, and we initialize a counter to count our defects as 0. We initialize that to 0, count underscore defects as 0. Next up we're looping in a range of defects dot shape and where, as I mentioned earlier, assigning the starting, ending and farthest points, right? So starting is in the form of tuples. Similarly for ending and farthest point, we're using that, and using our math library that we imported in our first few lines, we're going to be finding the distance between our starting, ending and farthest point. So you'll be getting three different distances. Okay, so we use the a square minus, so like we use that distance formula, Euclidean distance, and we use the math dot square root function to find the square root of the distance, right? So that's basically Euclidean distance for all these points, ending and starting, farthest and starting, and ending and farthest. Okay, so and I assign those values as A, B and C. Next up, I'm going to be calculating my angle. So I'm going to be using the cosine rule. If you don't know what the cosine rule is, please Google it. It's a basic 12th standard topic that you study in solution of triangles. So when you've got three angles of a triangle, you can find any angle of that triangle by using those three values. Okay, so it has a specific function formula for finding the angle, that is b square plus c square minus a square divided by 2bc, and we take the math dot a cos function to calculate that. Okay, so we got our angle. So what this does is, say this is your starting point, this is your starting point, this is your ending point, and this is your farthest point, the point marked in red. So it calculates three distances. It calculates three distances marked in blue and stores them into the A, B and C. Then using these values, it finds out this angle shown in blue here, and on the basis of that angle, it compares to the number of defects. Okay, so if angle is less than 90 degrees or equal to 90 degrees, we increase our defects by 1. So as you may observe, if you take your hand, you see that the angle between your fingers is less than 90 degrees. So if the angle is less than 90 degrees, that must indicate that there is a defect present there. That's why we are increasing our defects by 1. And if our defects has been increased by 1, we put a circle at that defect at our farthest point in our crop image, and that is a red colored circle, right? So we use the cv2.circle function, and we also draw a line between our starting and ending points in green color and thickness 2, right? So we use the cv2.line function. Next up, we're just, this is an if else block to check how many defects are there, and based on those defects we assign what number is being shown on your webcam, right? So if defects are 0, that means you only have one finger shown, so we print 1, right? We use the cv2.putText function. Similarly, if defects is 1, we show 2. If defects is 2, we print 3. If defects is 3, we print 4. And if defects are 4, we print 5, right? So this is a basic hand recognition program that only goes up to 5. You can extend it further if you want to, but you need to have different conditions for that. Okay, and we use the except in our try and except block as just pass. Okay, so next up we're going to be displaying all our outputs by using the cv2.imshow function. So first up we use cv2.imshow and gesture and frame. We show our frame. Next up we horizontally stack our drawing, which was our black background and our cropped image, and we show that as contours. And this is just used to break our program. So if Q is pressed, and it will see if the Unicode value of Q is equal to cv2.wait key, and if that happens, you will break out of your program. And last but not the least, we release our captures and we destroy our windows. All right, so that should so we've done with our program. So next up we'll try to run this, and a small caveat here that I have noticed is that if you have a plain background, it's generally better to get your output. So I'm going to run this now, and hopefully it should run. Yes, allowed webcam access to Python. Amazing. And I'll show this now. If I use a plain background as my notebook, you see that it prints 1 when I've got one finger. Now 2, 3, 4, and let me just take my hand slightly further. It should print 5, but there is some. Let's start again. So 1, 2, 3, 4, and 5. Yeah. So that's how you do that. So having a plain background works well. 1, 2, 3, 4, and 5. Right. So there are some errors that may happen, but this is generally how you do it, and it works like a charm. And if you see carefully between my any two fingers, you see a small red dot. That's our defect, and the contour around my finger is highlighted in green, and our hull is highlighted in red, the convex hull, and our white square is our initial frame, that our crop image basically. Alright, and we also have two videos, two outputs here that denote our Jesh threshold. Threshold was the black and white image, if you see. So you can see my hand there. That's what the computer figure sees, your program sees. And we also have an output called contours, right? So that's what my hand sees, right? You can see 5, and you see a contour on the left hand side of your output that has a convex hull marked in red. Alright, I'm going to be let's terminate our program now. So yeah, that's it for this video. Make sure to like, share, and subscribe if you found this video helpful. And yeah, I'll see you in the next video, and keep coding. See you guys. Bye bye.